Good morning. We are the Biosolution team and we are going to present our biomechanical device development. The goal of this study is to design a transtibial prosthesis for a 20-year-old cyclist in order that he can perform all the pedal movement and use safely the cycling clipless shoes, obtaining a useful life of about 2.5 years. For the concept development, the universal design methodology was used, starting with the objective established as the initial idea. Also, knowing the user needs, such as completing the cycling movement, ensure the balance and stability, and that is comfortable and lightweight. The requirements and specification of the prosthesis are that it is made up of a resistant material, adjust to the anthropometric parameters of the user, and ensure the use of the clip mechanism. And finally, obtain a conceptual design in SolidWorks and makes the finite element analysis.
Our HAT model is based on four key components, such as activity, human, assistive technology, and context. The activity factor is how the user do basic, instrumental, or advanced activities, in our case, mobility, such as road cycling and walking. Then we have the context factor, that is how the participation is activated by social, physical, cultural, and institutional means, and how it is maintained over time. For example, we have the physical, the need for a medical device that allows him to continue cycling, or the cultural, that is the relationship with his social circle. Then we have the assistive technology factor that includes the study of the interface of the system product with the user. For example, the environment, the pedal, the ground floor. Then how it contributes to generate the activity, that is mobility. Then we have the human, the motor. The loss of right lower extremely complicates mobility. Sensory, the loss of lower limb nerve endings that respond to external stimuli, and others. The table shown on the screen is the anthropometric measurements of our patient. Our patient is called Juan Carranza, and he has a weight of 65 kilograms, a height of 175 centimeters, foot length 26.5 centimeters, and others. After evaluating all the conditions of our patient, we design a sketch of our prosthesis that is shown on screen. We have socket, pylon, and foot for components, and a stump sleeve that we are going to talk about it more later. Designing and developing this type of medical device requires to follow and respect some regulation. Our prosthesis is based on the regulation that are shown on the screen to guarantee the quality, the safety, and the approval of use. Stump sleeve. For outdoors users, particularly with a high demand such as cycling, silicone is used without exception, as this material is very resistant. Some properties of these materials are shown on screen. It is flexible, suitable for sanitary use, high durability, resistant to high temperatures. We also see the tensile strength from 2 to 10, the elongation from 100% to 600%, and the biomechanical applications such as prostheses, tubing, and others.
The selected material for the socket and foot of our prosthesis is carbon fiber XL AS4A. The reason why we select this was because we were looking for a very high stiffness, strength, and lightweight material to guarantee the socket and the foot to resist loads of the body without losing the shape. The three main characteristics mentioned can be justified by presenting the properties shown in the table below, having a high modulus of elasticity, a significant elastic limit, and a low density. Whereas for our pylon, we selected the titanium alloy TI6AL4B, which, with its high yield and ultimate strength, allows the prosthesis to withstand longer to any fatigue failure and to develop a great mechanical resistance, taking in consideration that because of its low density, it becomes the lightest metallic material in the market, guaranteeing a lightweight prosthesis. Once mentioned the material selected, we present the design of our prosthesis with the use of SolidWorks. Here we're showing the lateral, frontal, and isometric views of it. Also, we present a little glimpse with the next video.
This is the free body diagram of the forces applied to the prosthesis. During cycling, we can observe that when the crank angle is 10 degrees below the horizontal axis, the maximum force applied by the muscle to the prosthesis is 803 newtons. A reaction force from the pedal is applied to the prosthesis in a 100-degree angle. The double direction vector indicates the rotation that the cyclist makes to unclip his shoe from the pedal. The right way to make this movement is shown in the picture below, where a torsion force is generated. Also, we consider a short period walk in which the main force is the weight.
Now we present our static and fatigue analysis. In this case, we implemented the use of the tools that SolidWorks give us. For our analysis, we took into consideration the following aspects. Studies show us that cyclists practice an average of 25 hours a week. They reach a speed of 90 revolutions per minute and they exert an average force of 803 newtons on the pedal. With this information, we can estimate a total of 7,246,250 cycles, considering that our prothesis has a 2.5 years life. Also, we consider the application of two forces, the first one of 803 newtons mentioned before and the second force of 2800 newtons, since this guarantees the visualization of significant structural damage compared to the first case, as there were no damages registered in our design by not applying a force with a minimum value in the SN curve.
The stress bond misses study shows the amount of stress applied to the prosthesis. This study is very important because we can identify if our design will suffer deformation when the value obtained is higher than the elastic limit. When 803 newtons are applied, we obtain that the maximum value is 18.5 megapascals located in the foot, which is lower than the carbon fiber elastic limit. For an applied force of 2800 newtons, the stress measured is 64.5 megapascal, concluding that the prosthesis structure and material selected are appropriate.
In displacement with 803 newtons, we can see that its maximum value is about 0.21 millimeters, so we can see a minimum displacement that doesn't affect the functioning of the prosthesis. With 2,800 newtons, we can see an increase in displacement, but this is still negligible at 0.74 millimeters. Talking about the strain, we have that with 803 newtons, there was a maximum strain of 0.0000563 in the arch of the foot of the prosthesis. For the 2,800 newtons, we have a value of 0.0001963. Despite the fact that the second is a little higher, the strain can be ignored as it's a very low value in both cases. When performing the factor of safety test, we can see that the entire prosthesis is blue, which indicates that it meets the value greater than 3 when exercising 803 newtons. In the case of 2,800 newtons, in the same way it can be observed that the prosthesis passes the test, observing the coloration that indicates values greater than 3.
Now, for our fatigue analysis, we consider testing the total life and the damage percentage. For an applied force of 803 newtons, we can see that the maximum quantity of cycles that our prosthesis will withstand is 100 million, presented in the blue regions, and the minimum quantity of cycles is 10 million, presented in the red regions. This means that our prosthesis has a total life of 1.5 years in these conditions. For an applied force of 2800 newtons, we have a maximum quantity of 100 million cycles, which is presented in blue regions, and a minimum quantity of 2,820 cycles, presented in the red regions. This means that our prosthesis has a total life of 0.5 years in these conditions.
This parameter of fatigue analysis represents the damage suffered by the model during the total life in which a specific event occurred. As mentioned before, the event is the daily practice of a pro cyclist. For the 803 newtons, the minimum damage percentage is 17, located in the socket, and the maximum is 172, located in the coupling. For the 2800 Newton applied force, which is considered excessive, we obtained that the minimum was the same as the one before, and a maximum of 611 in the foot.
In conclusion, the design of our prostheses have a good balance of tension, with a single exception on the arc of the foot, where the highest concentration is observed. This resulting in a decrease of the cycles of life of our prostheses. The main aspect of improvement is the geometry on that region to improve the balance and distribute it better in the arc of the foot.